So now we're going to look at an example that describes how to design logic networks for practical applications. So suppose that you were asked to design a combinational logic circuit for a security system for a house. We want the user to be able to select one of three operation states. So he will give an input for either activating a state in which which would be applicable whenever the occupants are sleeping. So when the occupants are sleeping, if one of the windows or the doors was opened, the alarm should turn on. So this is the first active state, or that the user can select. And here we are assuming that the windows and doors have sensors that can detect if they were opened. Another active state that we would like the user to be able to select is a state that would be useful in case the occupants of the house are away from home. In that case, the alarm should turn on whenever one of the windows or the doors was opened, or if a motion was detected in the house. And again, here we are assuming that there are sensors installed in the house that would capture any motion and send the appropriate signal accordingly. A third kind of state that we would want the user to be able to select is the disabled state, in which the user can disable the complete system, alarm system, so it will not turn on. And this would be useful whenever the occupants are at home. There are a few number of steps that can help in the design of digital circuits, similar to the one we are trying to design here. The first step would be to write quasi-static or quasi-logic statements, write the Boolean expressions based on the quasi-logic statements, simplify the resulting Boolean expressions whenever possible, then use also the Boolean algebra to write the Boolean expressions in all and or all NAND or all NOR kind of expressions. This would usually result in the minimum number of required integrated chip components. And the final step would be to draw the logic schematic for the electronic realization of the circuit itself. Back to our problem. So now we need to define the Boolean variables associated with the home security system. So we need to clearly identify the inputs to the system and the outputs. So as inputs, first of all, we have the user input. So as we said, the user should be able to select the state of the system, either state 1, which is applicable whenever the occupants are sleeping, state 2, when the occupants are out of the house, and state number 3, when the whole system is disabled. So since we are talking about 3 states, so we cannot just use one Boolean variable or a binary variable, because that would only work for 2 states. 3 states, it means that we need to have a 2-bit code or 2 variables. Each one of them can be on or off. This can be accomplished with 2 switches, so each can be on or off. Of course, this would give us 4 values for the code. However, we can disable one and then we just use the other 3. So in this case, we would call the inputs or the variables C and D. So this becomes a 2-bit code. And in case, for example, the first switch is on, the second is off, so C would be 0, 1, and this way the user would be in fact turning on state 1. However, when CD is equal to 1, 0, meaning that switch 1 is off, switch 2 is on, this way the second state will be operated. And when both switches are off, that simply means that we have the disabled state active. So this is the first input, which is the user input represented by C and D. Then we have also the state of the doors and windows in the house. So when the one of the doors or input or windows is open, as indicated by the attached sensors, then the state should be 1. Otherwise, it will be 0. So for that, we would need only one binary variable. We call it variable A. And again, it could have a value either of 1 or 0. 1 is active, meaning that one of the doors or windows is open. Otherwise, if it's 0, then they are all closed. Then we need one more variable, Boolean variable, or a binary variable, which we would call B, and this would represent the state of the motion detectors. So if there is a motion detected in the house, it will give me a reading of 1, otherwise it will remain 0. So these are the inputs here. So we have the C and D representing the user input or selection. Then we have A and B representing the sensors, the ones associated with the windows and the doors, and the ones associated with the motion detection. And when it comes to the output, in this case, we have only one output, is either having the alarm on or off. So for that, we would need only one binary variable, which we would call it Y. And whenever it's equal to 1, it means the system is active. It will be giving the alarming sound. Otherwise, if it's 0, it will be off. The next step now would be to write the quasi-logic statements. So our understanding of how the system would work should be written in a concise, precise sentences describing how the system works. So in this case, we would like the alarm, the output variable Y, to be equal to 1. So the alarm would be activated if A is equal to 1, which means that the sensors has detected an open door or window, and the user input code was 0, 1, which means that the already user has selected state 1, active state 1, and because the occupants will be sleeping and the door was one of the doors or windows was detected to be open, in that case the alarm will turn on. In addition, the alarm because we have an OR here, the alarm will turn on also in the case where if A or B, which means one of the doors are open and the doors or windows is open, or there was a motion detected in the house when the user have selected active state number 2, which means that which corresponds to the case where the occupants are outside the house. So what you can see is important here, and underlined the words and the words or, because these will be translated into the Boolean expressions later on. Now the goal is to write the quasi-logic statement that we have in a Boolean expression. And we will do this in two steps. The first step is to further simplify the quasi-logic statement. So we try to remove as many words as possible. So we'll have Y equals 1 here, which corresponds to activating the alarm. And this should happen when A is equal to 1 and the code CD is equal to 0, 1. Or Y will still equal to B1 if A or B is equal to 1 and the code CD is equal to 1, 0. So what we have here are basically the logic expressions and, or, and giving values to the Boolean variables. Then you need to realize if you want to write the whole statement in a Boolean expression. So you on one side you should have y, and on the right side the expression should be equal to 1 to satisfy y equals 1. And that would only happen if the active state code CD is given a value of 1. So here if we replace this with 1, and if we replace the active state 2, which is CD, if we replace this with a value of 1, so together the expression on the right will give a value of 1, because 1 and 1 will be the logic 1 and 1 will give me 1, and the logic also of this being 1 or 1 would also give me 1, and when you have here 1 and 1 would also give me 1. So as a total, the whole expression on the right would become equal to 1. And however, in order to find to give a value for the active state 1, CD 01, to make it equal to 1, the best way to do it is to use this expression where you are inverting the C. So in this case, the C had a value of 0. When you invert it, it becomes 1. And when you say 1 and 1, so the logic expression would be equal to 1. And the same thing here for CD. So you just want to invert the 0 to 1, and then apply again the AND logic. So 1 and 1 would be will be giving me 1, and this way the whole quasi logic statement can be represented with the Boolean expression here in the box at the bottom, where you can see the AND becomes a dot here because this is the mathematical expression for the and the OR here becomes like the plus sign. Another OR is the plus sign, and they have the AND here as being this dot. So now at the top here we have the Boolean expression for this digital circuit. And one thing we can notice is that if we construct the truth table for the CD and C over bar and D expression, and the C and D over bar expression, what we would notice is that C over bar and D expression would give me the same values as D, for example here. And if you look at the second expression, which is C and D over bar, it's giving me the same values as C. Of course, this is in this case it's working this way because we neglected the third case, the fourth state, in which both C and D are equal to 1. But we remember that we disallowed this state, so we cannot have both switches on. So that means we can replace in the Boolean expression equation, we can replace the C over bar and D with simply D, and we can replace the expression C and D over bar with simply C. This would really simplify our Boolean expression for this digital circuit. Looking at the simplified Boolean expression, we can see that it contains here we have an AND, an OR, an AND. So we have two AND logics and two OR logics. Usually it's preferable to have the expression using only one kind of logic, and that's because the logic gates, they come pre-packaged on integrated circuits, usually in groups of 4 or 6, and it will if you have all of the logic expressions to be the same, there's a possibility that you would minimize, this way you will minimize the number of integrated circuits needed. Now, how to convert from one kind of logic gate into another? This is usually done with the De Morgan's laws. So, for example, if I want to change the OR logic gates here into the AND logic, this can be done by inverting each variable, so each one of these variables A, B, C, and then interchanging the logic gate and then inverting the whole expression. The same thing if we had AND and I want to exchange it with the OR. So you can do that by inverting each one of the variables and then inverting the complete result after interchanging the logic. So this is how we apply the De Morgan's laws. So first of all, we want to replace the OR gate here with an AND gate. So notice how each of the two variables were, each one of them was inverted. The OR becomes an AND, then the whole expression was also inverted. Then what we do is we consider the other OR logic and we want to turn it into an AND. This would be done by inverting each of the individual variables. So this one becomes inverted. This part would become inverted. This part, the whole part here would become inverted as indicated with this long over bar. And then the whole expression is, the resulting expression is inverted. So this would be the final Boolean expression for our logic circuit. Now the next step would be to draw the circuit diagram, and this is done by step by step taking each of the sub-expressions and drawing them and connecting them to get the final output y. So you can see we have these vertical lines representing the different inputs A, B, C, and D. And if you look at the first sub-expression here, A and D, so this is represented by the AND logic symbol here, A and B, then I need to invert the result with this symbol. And let's stop here, then move to the other expression, sub-expression. You start by inverting A and B, as you can see. We're drawing from A, inverting it, and drawing from B and inverting it. Then you apply the AND logic here. Then notice that you would need to invert the result of this sub-expression as represented here. Then you need to apply the AND with the result with the input C. So we have here the AND and also an input C. And notice that you need to invert the result as indicated here. And finally, you need to apply another AND with the previously obtained result for the sub-expression here. And the output would be finally inverted as indicated by the long over bar over the whole expression. And this would be the result y. Now to realize the circuit, the digital circuit that we constructed, we would need two integrated circuits, the 7408 and the 7404. Notice that the first, the 7408, has 4 AND gates, exactly as what we need in our circuit. And the 7404 also includes 6 inverters, exactly as many inverters as we need in our circuit. So these two integrated circuits would be enough to realize the digital circuit for the security system. It's worth mentioning that the Boolean expression that we had before applying De Morgan's laws included 2 AND gates and 2 OR gates, which would require 2 integrated circuits to construct our security system. So in this case, the all AND realization that we got after using De Morgan's laws did not reduce the total number of integrated circuits required. However, in general, using a single type gate realization would reduce the total number of required integrated circuits.